Have you ever wondered what makes a YouTube video successful? In this video, we'll carefully look at the graphic, demographic, and social aspects that might make an upload appealing. Just kidding, we'll cram a bunch of YouTube data into a neural network and see what it spits out. Alright, so we want to train a machine to understand what makes a good YouTube video. To do this, we'll take a lot of public information and feed it an AI model. Then we'll ask the model to predict whether a video will get loads of views or be forgotten forever. Okay, so to train the AI model, I first need a large number of examples to feed the machine so it can learn, pick up on patterns, and make predictions. I use publicly available data on tons of anonymized YouTube videos and fed the model information on every video's length, days since upload, like to dislike ratio, and comments to reaction ratio. You'll notice only one of these 4 variables is actually within our control, which is how long we make the YouTube video, and we'll come back to this later, but for now I want to focus on what YouTube considers important. Now before I go into the juicy machine learning parts, I figured I'd take a look at some trends. I went into the data, grouped it into buckets, and plotted nice little charts to show you roughly how the variables that I chose actually correlate with view count, and here's what I found. Okay, so the first thing I looked at was video length. You might have heard that YouTube really prioritizes watch time, and longer videos have done well on the platform for quite a while. And it's good to see that that's mostly validated by our data. It seems that on average, as you make your video longer, it will get you more views, but careful not to make it too long because you will start to lose viewership. The sweet spot from this data seems to be between 15 and 20 minutes. Another interesting thing is it doesn't seem like shorter videos necessarily do badly. Rather, they all do similarly worse below the 10-minute mark. Moving on to the comment section, we find some interesting trends. This is one of the strongest correlations in our data, and it does exactly the opposite of what we'd expect. You can see that the more comments there are compared to likes and dislikes, and the worse a video actually does. This could be because YouTube wants to prioritize watch time, not time spent typing, or wants to reduce debate and controversy in the comment section, or it could just be noisy data. If we shift the likes and dislikes, the more well-liked the video is, the less views it can expect to receive. Why is that? Moving to the end of the list, we have the number of days since you've uploaded your video. Now, we'd expect the more time passes since we upload and the more views we rake in. Is that the case? Kind of. Seems like as soon as you upload, you can expect a nice view boost, and this is probably mostly dragged up by bigger YouTubers who get most of their viewership from their strong subscriber base in the first weeks of upload. If we look past that short-term boost, we go back down to a lower average level of views from smaller YouTubers, and these smaller YouTubers can expect to see some very noisy growth in views between the first weeks all the way down to almost 2 years. So if you haven't hit that 1 million views in your first week, there's still hope. Now, trends are super useful at telling us how each of these things behave individually, but they're not very good at telling us how they behave together. For example, we said longer lasting videos do tend to perform better, but what if they have a ton of dislikes or really few comments? That's where statistical models come in. Sorry, I meant artificial intelligence. We'll soon be training our own model and seeing how it makes sense of all this complexity and how these variables can interact together. Okay, so now I'm gonna feed all of my variables into my model, which is gonna be a neural network, and start training it. Alright, so the model has had time to train itself on a bunch of examples. Next, I'll be feeding it some videos it hasn't used for training and see how well it predicts how many views those will get. To calculate how good or bad the model is at doing this, we need something called an error metric. An error metric is just something that quantifies how far off the model's guesses of how many views a video will get are from the true views that that video got. I'm going to use something called median absolute error. I'll put the formula up here for the stats geeks, but suffice it to say, it's just the simplest possible error metric, and it will just tell you the difference between the model's prediction and reality. The higher the error metric, the bigger the difference between reality and prediction, and the worse our model is. So how'd the model do? I'm running the results right now, but I'm sure it's gonna be great. Pretty much everything I code is great and just knocks it out of the park. And it sucks. I just finished running the results and they don't look as positive as I thought they would. I'll show you what the actual code looks like here. Okay, so this section right here is where I actually train the model. Here I'm calling a custom class that I built to train all my models. I first pass it the dataset that we talked about, then I'm gonna tell it what model to use, and at the very end I'm gonna tell it what it needs to predict, which is the total view count of every single video. These next few lines just call the class and train the actual model. This is where the model learns patterns in comment ratios, like ratios, video length, and tries to see how they correlate with view count to make a prediction. At the very end, I'll be feeding the model some videos it hasn't used for training and see how well it actually predicts how many views those will get. I've stored all the final results in this performance data frame, so let's open it up and take a look at what ended up happening. I'm going to type it up right here. There we go. So the number on the left shows you the median absolute error. This is the error metric that we mentioned before, and it's 7,200. What does that mean? That means on average, when the model is making a prediction on an unseen video, it will be wrong by about plus or minus 7,200 views. Now that sounds really, really high, and it definitely is a little bit high, but my sample has videos that range from just a couple of views to a couple of million. So relatively speaking, this number isn't actually too bad. To make this a bit more scientific, in statistics, when you're making a prediction, you always want to compare your model to some simple benchmark to see if it's any good. In our case, I created a dummy model that always predicts every video will have as many views as the median view count in its training data. So every time it's just saying that every single video will have the same number of views, and that number of views is just the median of its sample. The median error of this model is this second column that you see right here, and it turns out it's actually going to be wrong by plus or minus 8,800. That's way bigger than our model's error, and it means our model actually improved prediction error by a whole 18%. Some of you might be saying, well, of course it's better than just predicting the median, that's such a bad prediction. And some of you clearly haven't worked in data science, spending weeks building a model that can barely outperform a simple moving average or a lag Y variable. If you know, you know. And something that we need to be aware of is this model is just training on video length and some like ratios and comment ratios. It doesn't know anything about the historical views of that channel. It's really limited in the scope of predictions it can make. Okay, so a good first attempt, but not perfect. I decided to spend some time to really get into the model and look at it deeply to see if there was any errors or anything that I could improve. Nope, all looks good to me. So I'm going to move to a much more promising approach, which is classification. Classification is still a prediction task, except unlike our previous approach, which was a regression approach, we're no longer interested in knowing exactly how many views a video will get. Instead, we just want to know if the views will be above or below a certain threshold. Let me explain that in a little bit more detail. And if you already know about classification or you don't care too much about the technical side of things, you can skip ahead to this timestamp just to see the results of this different new model. And spoiler alert, they're really good. Now, for the scholars among you, let's say we have this made-up graph of video length on the horizontal line to YouTube views on the vertical line. Now, I'll sample 2 points, and they seem reasonable. The shorter video has lower view count, and the longer one has more views. That's consistent with what we've seen. Let's assume I was using some linear model just to make this simple. In that case, what the model does is draw a straight line between the points, and now we'll make predictions along that line. So from our points, we can see a video with 400 seconds in length will make about 20,000 views. A video with 600 seconds in length will make about 30,000 views. And if I keep predicting along that line, a video with 800 seconds in length will make about 40,000. Now, this applies to the data the model has used to create that line, meaning training data. But if I sampled a new point from the real world, so a video that the model hasn't seen to train itself, it obviously won't fall exactly on that prediction line. Otherwise, we'd be fortune tellers. It will fall somewhere to the right or to the left, meaning there's always some amount of error compared to what the actual true view count will be. This gets even worse if our data is not well behaved. For instance, let's say I sampled these 2 new points. All of a sudden, it's not very clear what impact video length even has on view count. We see that if a video has 500 seconds in length, it might make 45,000 views, or it might make 65,000. It's kind of hard to tell. If I had to draw a new prediction line for the model, it would look something like this now. You can see it's a lot steeper. And what that means is if we go to sample a new real world video that the model hasn't seen this time, it will be even more likely to have a big error, because even a small deviation to the left or to the right of the line means a really big vertical deviation in terms of the number of views. So how can classification help? Well, in classification, we're only ever interested in knowing if view count is going to be above or below a certain threshold. So in our graph, if I wanted to know if a video will be above or below 25,000 views, do you see how that might be separable? All we have to do is draw this straight line right here. And you can see anything to the left of the line will have less than 25,000 views, and anything to the right of the line will have more. Now, the accuracy of this model, at least in its training data, is going to be 100% because we've perfectly separated out what videos will have less and more than our prediction threshold. Now, you might be asking, the problem with the previous model was not existing data, but sampling new data. So what would happen in this case? Now, it's still completely possible that we sample new data and it doesn't conform to our prediction line. Now, that's true, but let's look at the areas. Before, any small deviation from our prediction line would result in an error. Now, we can actually be very far from our prediction line and still have 100% accuracy. What do I mean by that? If I sample a new point, a new video, it can be anywhere in this quadrant, and I can still have 100% accuracy. Likewise, on the flip side, I can sample a new video that has more than, let's say, 500 seconds in video length, and all I have to do to still be 100% accurate is for that video to have a view count that's above 25,000. That's a huge range. All of a sudden, I move from a small deviation resulting in a really, really big error, no matter how small the deviation is, to having this big area of effect within which I can still sample and be correct. Now, obviously, this is made up data. No model tends to be 100% accurate in its training data unless it's overfitting. And also, again, it's perfectly possible for us to sample in the wrong quadrant and decrease our accuracy. And this is even more likely as problems become more complex, or as you have more than two classes in a classification problem, and so on. But hopefully this example set a bit of an explanation for why it's actually easier sometimes to work with classification than regression, if the problem that you're working with actually has a use for classification. In our case, it's useful to know if our video will do good or bad. But you might have tons of cases where actually all you need to know is the actual predicted number, and knowing whether you're above or below a certain threshold is pretty much useless. Okay, so now that we have a good understanding of what classification is, I'll go back and retrain my model to predict whether a video will get above or below 1,000 views. The infamous mark below which I don't think anyone clicks on your video unless it's by mistake or to know how other struggling YouTubers code. I still kept most of the code framework that I had from before, except I switched the neural network out for a random forest model. This is just a different type of machine learning model that tends to work well for bounded classification problems, which is what we're doing. The output of this new model is just going to be a 0 or a 1 for whether the video is going to be above or below 1,000 views. Okay, so I'm rerunning the model right now. So I'm just going to show you the code and see what we're doing here. Basically, it's going to look very similar to what we did last time. I'm using the same sort of parent class, except as we mentioned, now we're going to be predicting a 0 or a 1 instead of the actual view count. The part where I do that is right here. So you can see I set a threshold, which is above or below 1,000 views. Then here we have the same class as before. I'm going to call it for the new data set with the 0 or 1. This time I'm going to pass a random forest model instead of the neural network. And then I'm going to tell it to predict, again, 0 or 1 instead of the total view count. I haven't actually run it yet. Let's see how this goes. All right, so that tells us it's running. It's trying all the different combinations, and there we go. This is just a curve that shows you how well the model is doing. If it's cuts from 0 to all the way here, just as a straight line, it means the model is useless. The more it arches this way, the better the model is. In theory, a perfect model would just have a line that goes up and then across. So this is actually really, really good. To see in more detail what the actual performance of the model is, let's take a look at this cell. And there we go. Okay, so this is going to tell us the actual performance. So here we have the accuracy of the model, which is 92%. So basically it's going to be 92% accurate at telling me if a video is going to be above or below 1,000 views. That's pretty sick. There's a few other numbers here. I'm not going to go into too much detail on the maths, but basically these two are quite important. The sensitivity, think of it as an accuracy that goes from 0 to 100%, just like accuracy, but it's very specific to predicting whether a video will be below 1,000 views. Specificity is the same exact thing, except it's the accuracy of predicting when a video is above 1,000 views. So this is really, really cool. Now, as a disclaimer, as we mentioned, this model is a little bit more limited than the previous one. It can only tell us if we're above or below a certain finish line. But that's massively useful if all we want to know is if our video will be popular or not, or to set a minimum number of views that you can guarantee to a video sponsor. Okay, so what did we learn today? We learned that regression problems are hard unless you have loads of data and variables, but we saw that we can build a really good classification model with incredible accuracy using just a few common YouTube metrics. All right, guys, that brings us to the end of the video. If you liked it, please make sure to leave a like and subscribe. I have a lot of good projects waiting for you. I really enjoyed making this video, but it ended up taking way longer than I thought. I do all the filming, editing, color grading, thumbnails, and graphics myself. Pretty much everything you saw here today except the 10-second video intro was my own work. So if you think you might enjoy other videos about AI, make sure to subscribe and turn on notifications. It really goes a long way. I've also left some links in the description to some of the gear and programs that I've used to film and edit this in case you are interested in making your own videos. See you next time.